Welcome to solverfy.
Okay, so for this problem, it's saying that G is a simple graph with n vertices. So part A is saying that G is a tree if and only if it is connected and has n minus 1 edges. So because it's an if and only if, there's going to be two parts to this proof. There's going to be a going from the left to right statement, an if-then statement. The second half of this is going to be an if-then going from right to left. So I want to just kind of talk about a few things. So for the going left or right, I can simply state the tree definition. So it's saying that there's connection and no circuits. So I can use both of these to my advantage. So going from left to right, that's half of the proof right there. It's just stating that definition. And then doing for the left side, if I have n vertices with n minus 1 edges, then I can use induction proof to prove that that is actually the case. Now going from the right, again, the connection being a tree, that kind of fits in together. But I kind of want to bring in the whole entire circuit thing. So I'm going to kind of do a negation and kind of suppose that so in the sense, I'm going to suppose there are circuits. And what I'm going to do is I'm going to remove those until gone. So what I want to show is that I can only, if there are n vertices, so n vertices, then I will be removing n minus 1 vertices until I get to the point I can't do that anymore. So once you remove the circuits and there's connections there, then there's going to have to be n minus 1 edges. Okay, so I am going to go ahead and start on the proof. So going for the left direction, again, I'm going to state my tree definition. So if G is a tree, there is one vertex. Sorry, then there is, then it is connected and has no simple circuits. So then I want to use be performed. So I want to talk about how it's going to be induction proof. So when n equals 1, then there is one vertex. Okay, and no edges. So n minus 1 going to be 1 minus 1, which is going to be 0. We want to assume that the n equals k statement holds. For n minus 1 equals k minus 1 edges. Suppose he has k plus 1 vertices. I'm going to let vertex be, because I want to show that if I remove a vertex, it's going to become k vertices, which would then be k minus 1 edges. So I'm going to let vertex be a leaf for parent vertex A. So if B were removed from G, then G prime would be produced, having k vertices. G prime would still hold connection with no circuits. Then G prime would have k minus 1 edges. Thus, G is a tree if it is connected with n minus 1 edges. And the first part of that is completely done. So then for the right direction, let's say let G be a connected simple graph with n minus 1 edges. So I'm going to go ahead and just say that that's the case. So it's connected, it's got n minus 1 edges. So I want to go ahead and negate this and show that there's, okay, so suppose G is not a tree, then the removal of an edge would keep G prime connected as there is a circuit present in G. So taking that out does that. Um, Now suppose G prime is not a tree, then the removal of an edge would keep G double prime connected as there is a circuit present in G prime. So the process, okay, so this process would continue until a connected graph is obtained with no circuits. Okay, this would require at most n minus 1 steps as there are n minus 1 edges to remove. Thus, n vertices exist in G, and G is a tree. And of course, that would be the end of the proof. Now for part B, this one's going to be a little bit different. So first off, the left to right is going to be the same as part is A. A's left, basically. So we can just refer back to that one and call it a day. Now, as far as the right going to the right direction, okay, so for the right direction, the problem actually gives us a hint in it. So it tells us that we need to show that that G is connected if it has no simple circuit and it's n minus 1 edges. So we need to show that it cannot have more than one connected component for each vertex. Okay. So in order to do that, what we need to do is this would be a good opportunity whenever you have something that's gonna it's not you're gonna have no more than a certain number. You always want to do a negation type of proof. So suppose it does have what it's not supposed to have, or what you're trying to prove that it does. And that way, if you can prove a contradiction, then you can, continue on. So for this one, this is the same proof, or this has already been proven in part A of this problem with the direction proof. And so now we can just jump into the right direction. So what I want to do is I want to identify, so let G be a simple graph with no simple circuits and has n minus 1 edges with n vertices. I want to suppose, this is where my doing what I'm not supposed to be doing, has more than one connected component such that any two vertices, such as C and D, would have two possible paths. So if they have two possible paths, that means that then G would contain a circuit, which is a contradiction. Thus, G is a tree if and only if it has no simple circuits and has n minus 1 edges. And that's the end of the proof.